All kinds of is it?
We're printing a little, it's like, a lot of times spots, but.
Oh, cool.
And that's just. And we're gonna be a little baby rocket.
So you like ready? Like ready? Wait, so I don't need to get more.
Guys. Yeah, so it's the.
Oh, man. So that's all the channels of that. It's like this high.
You can have like.
Yeah, I know. And
He sat in that class on his whole time. Oh, really?
What?
What was that, Sean?
Yeah. You see the little tiny rocks? They like that. That's a lot of stuff. See it now. They never find out. Even like my son, they switched to shit to art setting, and I was like, he's like, it's just too bright. You're on dark, you want to go walk back. How does that work? Like when you're parking there, you smoke a lot of soda. I didn't really do a lot of so yeah, my boy and I use we have to make like a lot of like oh my God. That's you're not oh, I just hope you never do it. I know. Even if it's not red, it's damn. It's good also then. It's like 10, 15, or like 20. But like, was 14. Can you imagine if you were 13?
Yeah, you're like, I'm not gonna be too nice right now. For yesterday. This
I read out like.
I know. You can't find it.
No, but I've heard some there.
Yeah, that's gonna be the worst feeling. At first, you're like, go further going.
Was the neighbor upset?
Outside, like, you I wonder if there's like one neighbor. And just like.
Oh, yeah, great.
Yeah, that's too random.
Yeah, we have to make up.
Oh, it's like what if it's like four like. Yeah. Small out.
Yeah.
Very good.
So they only so
Close broad.
yeah, if they want to like be like buy the books, like and then an extra 100 is for your. And then we'll use this. Oh yeah, I think computers ever like.
Alright, it's 5:30, let's go ahead and get started. Alright, good evening, everyone. How's everyone doing today? Good. See smiles, that's good. It's generally a good thing. Alright, so let me address something. I think I've gotten a lot of emails on this, and so I know that there's quite a few of you still on the wait list. So let me give you an update on that. So on Friday, I put in a request to add all 16 people on the wait list that were on the wait list as of Friday. If anyone added after that, too bad. But if you were one of the 16 people on the wait list on Friday, I did request that we add everyone here. And so the reason that hasn't happened yet is because it kind of goes, whenever we change the capacity of a course, it goes through the department. And right now the department is focusing on getting students into the required courses. So making sure everyone's in a section of senior design, making sure everyone's in a section of a lab that they need for this semester. And so, they haven't gotten around to the electives yet. On Friday, the department said they would try to get to the elective courses early this week. But we're at the end of Tuesday and I consider that to be the early week, but I think before the end of this week, for sure, then they should be able to get to it. But kind of the other issue that's kind of unique with this class is that adding 16 people from a wait list is a lot. Which for me it's not a problem. I've had classes with 50 students before. It's just kind of when you kind of balance, generally we like to balance the load between other similar classes at the same time. And so that may be the other reason. But at this point, by the end of Tuesday, you guys have already done 3 lectures with me. And everyone that's been on the wait list has been attending the lectures. At least, this room is very full from what I can see. And so, it gets more and more likely that you guys will be at it because everyone's been attending and participating in the class. And so I would say just kind of sit tight for now. I know you guys are a little bit nervous about it, but I'm hoping to have an update for you before class on Thursday. So I'll check in with the department again tomorrow and see kind of where that's at. And get that. Okay. But that's kind of where that is right now. So that's kind of why a lot of you are still on the wait list. So if you're on the wait list and you're not part of the Canvas site yet, shoot me an email. I can at least manually add you to the Canvas site, so you'll at least have access to all the course content. So I can at least do that for now, and then hopefully before the end of the week you'll be added officially. Okay, and so I think that's my only announcement. So the plan for today. Today is our first, I guess, more traditional lecture. And so, last Thursday we did our first ANSYS activity. A lot less chaotic than I thought it was going to be. Usually the first activity is more chaotic than that. You guys did a really good job. So remember that first activity is due this Friday. So make sure you guys are working on that. If you're having trouble installing ANSYS on your home computer and you want to work on that at home, let me know. We do have an option for you to kind of virtually log into these computers. And then I have a video that kind of shows how that is. Okay. All right, and so I think that's all my announcements. Are there any questions I can answer before we get started for today? Yes.
You be working on the homework at all today?
No. So today we're just going to be lecturing the whole time. So and so generally for the activities, I dedicate a full class session to do the activity to kind of instruct you, and then once that's over, then whatever you don't finish is homework based. Okay, all right, so let's go ahead and get started. And so the topic for today is, I kind of call it the theory behind FEA, which kind of does it a disservice a little bit because there is a lot more theory behind FEA. But we're not going to be doing too much of it in this class, and so that's why this is a lot of what you need to know about the theory. It's at least a SparkNotes version of it. That's what you can kind of think of it as. Okay. And so even though in this class we're going to be focusing the majority of the class on the application, and so we're going to be focusing a lot on ANSYS. It's still this is still a traditional class in FEA, so we still need to know a little bit about what's going on behind the hood, of what I like to call of ANSYS, a little bit of a theory, exactly what's going on, so that you're not just kind of this class is more than just pointing and clicking within the software. Okay. And it's useful too because like we talked about in the very first class session that when you guys leave this class, I want you guys to have the confidence that you guys are experts in FEA. Okay, and part of being an expert is knowing exactly kind of what FEA is actually doing, right? Maybe not the exact mathematical details of all theory. You should at least kind of know what the computer is actually trying to do when it says it's solving your system. Okay. Okay. And so you might be surprised to hear this, but at its core, finite elements. The finite element method has absolutely nothing to do with computers at all. So it was actually developed kind of way before computers was really a thing. Question from Zoom? And actually, when the theory of FEA was kind of first developed, people kind of ignored it for a long time just because it wasn't useful. It wasn't really until computers kind of came along that it really became useful. But the whole idea behind FEA is that it's a mathematical technique for transforming differential equations into algebraic equations. And so it's basically a form of transformation. Okay. It's in reality it's a lot more complicated than that, but that's generally its main scheme. And so kind of the first papers of that kind of propose this idea of finite elements kind of wrote it like the following. And so this was during a time when it was kind of being discovered that a lot of physical phenomenon, things like structural mechanics, heat thermal mechanics, heat transfer, fluid mechanics, the behavior of a lot of these systems are governed by differential equations. And so, for example, I have here kind of the heat equation, one form of the heat equation. Okay. And so here we have a differential equation. So there's a lot of very well established theory, that you may be learning right now in heat transfer 407, or maybe you took 407 last year, that says that by conservation of energy, the way thermal energy moves in a system follows this equation right here. Okay, and that's very well established. The problem with an equation like this is that this is hard as hell to solve, right? And so this is not an easy equation to solve, at least by hand. And so the idea with FEM, or FEA, FEM, same thing, okay, is to be able to take a differential equation like this, when we solve it on a domain. If you break up that domain into a bunch of tiny elements, you can transform this into a very large algebraic system. Which traditionally, for most algebraic systems, we express it in matrix form. Okay. And so we have A times X is equal to B. And when I say large, I mean very, very large. So, I think, probably from your linear algebra classes, a large linear system to you may be, 3 equations, 3 unknowns, 4 equations, 4 unknowns, 5 equations, 5 unknowns. These are much larger than that. So this is like hundreds, thousands, tens of thousands, hundreds of thousands of equations. Okay. So this might be, 100,000 by 100,000. 100,000 equations by 100,000 unknowns. Okay. And so that's kind of the basic idea of FEM, is to take a differential equation and transform it into an algebraic system equation. Okay. The problem with this is that before computers came along, is that very much like the differential equations, a very large system of algebraic equations is also extremely difficult to solve, right? And so we're not really saving us any work here. Right? We're just going from one extremely difficult problem to another extremely difficult problem, except that along the way, we apply this extremely difficult method known as finite element methods. And so, when FEM was kind of first proposed, the mathematics behind it were sound. And so they were able to publish it, but there were just no real good practical applications of it just because, of the difficulty in solving this large system. Okay. But things started to change, when computers started becoming a thing, and we're able to see, how computers can be used to solve these systems. Okay. One thing that computers in particular were very good at was solving algebraic problems. And the reason for that is that, the way or the algorithms that you use to solve algebra problems are very repetitive, right? And so they require a lot of, by themselves, each step is relatively simple, but it requires a lot of these steps kind of over and over and over again, right? And so that's what computers are really good at. Computers are very good at very simple calculations, but they just do them extremely quickly. They can do thousands, hundreds of thousands, millions of equations in the same amount of time that it takes a human to do them as well. Okay? So computers are actually very good at solving these kinds of systems. And so this is when FEM really started to take off. And so, we have these, physical systems. We know that their behavior is governed by differential equations, but those differential equations are very difficult to solve. Okay? Even for computers, computers can't really solve differential equations, at least in the way that we solve. Okay? But if we take those differential equations and transform them into algebraic systems, then that's something the computer can solve. So FEM gave computers a way So FEM gave computers a way to solve these differential equations, which was kind of massive at the time, right? Because on the one hand, you have one community of scientists that are saying, all these physical phenomena that we kind of observe in the real world, their behavior is governed by differential equations, but they're really difficult to solve. Whereas, in another area of science and research, they're saying that, we can take these very complex, differential equations, transform them into algebra equations, and then have a computer solve them. And then, so once those two communities kind of, married each other, then modern FEA, as we know, was kind of. Okay. All right, and so from this, we were able to kind of, obtain, what I consider to be kind of the engineering application, the engineering use of FEA. Okay. And so I have it kind of laid out as kind of a flow chart. And so actually, let me label this first. Call it modern engineering use of FEA. Okay. And so when you're using FEA from an engineering standpoint, most of the time, you're starting with some physical system of interest. Whether this be the car that you're designing or whether it be, a bridge that you're analyzing, you have some kind of physical system, okay? And then from that physical system, it has its own set of governing differential equations. And so those governing differential equations are what's going to determine its behavior, okay? And so it's going to determine how the system responds to loads, how it responds to constraints, so on and so forth, okay? And if you're going to do any kind of design or analysis of these systems, you have to be aware of what those equations are. Okay. And so from here, what you would do is that you would take those governing differential equations, you would try to solve them using FEA. So from here, this arrow right here in particular is FEA. And so through FEA or through using ANSYS, you would take those governing differential equations, apply it on your domain of interest, so on your geometry, and then you would obtain an algebraic system of equations. Okay. And then once you have that algebraic system of equations set up, then you can use computers. Computers are really good at doing algebra, and so it's able to solve this system for you. Okay. And then from that system of from that solution, that solution to the algebraic system of equations is what I call kind of a raw solution. So in its form, kind of by itself, it's not really readable by humans, or it's not really usable by an engineer. So there's an additional step here, which I call post-processing, that's most of the time done automatically by the computer. Okay? And what it does is that it takes that raw solution and then presents it in a form that's useful to the engineer. Okay? And so from that, you're going to obtain what I call the engineering results of interest. If Zoom can catch up. Right, and then from those engineering results of interest, so these are things like, stress distributions, deformations, things like the results that we found from our first activity. And so what you do then as an engineer is that you take that information, and then that's when you perform your design and analysis and safety analysis and things like that. Okay. This flow chart here kind of gives you an idea of how kind of modern FEA is kind of is usually performed by an engineer. And so FEA, FEA is, and we've kind of gone over a brief history here, but it's kind of gone through a lot of transformation. The nice thing for you as a user of FEA is that a lot of this is handled within ANSYS itself. Okay. And so I'm talking about, these very large, these very complicated equations, these very complicated, algebraic systems, but if you remember from activity 1 last week, you saw none of that, right? So all that was handled within ANSYS itself, right? So these 4 boxes here, these 4 boxes that I've kind of, I've highlighted with an even bigger box. All of this is usually handled by commercial software. So all of this is handled by ANSYS, and you see almost none of it. And so for you, all you really see is that you see a CAD file, you see a mesh, and then, like 5 minutes later, you see deformation, stresses, and all that stuff. Okay. But in reality, what's actually happening is all of this kind of very interesting kind of mathematics and kind of programming under the hood. Okay. It's just that ANSYS has kind of packaged it in kind of a very user-friendly format, so that you don't have to deal with any of the math. But it's still useful so that so that next time we do ANSYS for activity 2, when you hit solve, you know that ANSYS is actually doing a lot underneath the hood for you, in order to get you the solution that you pick. Any questions on this? All right. And so, I think that's useful to know just from just from a perspective of a user of the software. Okay. But this also gives you some interesting insights into what else FEA can be used for, right? Because when you use FEA as strictly a user of ANSYS, you may think that you're restricted to the kinds of analyses that ANSYS tells you that you can do. So things like static structural, transient dynamics, or thermal fluids and stuff like that, right? But that's not true, right? So FEA can actually be applied to any differential equation. And so, of course, most of the time we associate FEA with kind of physical systems and their governing equations, but in reality, you can solve any differential equations. And so, you'll see an occasional paper pop up from like a theoretical math group that have this like very complicated math equation that has no physical significance at all. But the only way that they'd be able to solve it is using FEA. Okay? But this also opens up the possibilities for new equations as well, right? And so you'd be surprised. And so I think what you learned from your other class is that let's say heat transfer, right? The heat equation is the only equation that you can solve for heat. But that's not necessarily true, because even though that heat equation may be good for the majority of cases, you may have very niche cases where maybe you're solving for heat transfer in a material that's melting in real time. And so you have kind of different states of matter that's going on. Or maybe you're solving for heat transfer in a very fast moving fluid. And so you need to solve for fluids and heat at the same time. And so when you have these kind of multi-physics or multi-phase kind of situations where you have even more complicated equations, you can use FEA to solve these. It's just that you have to write the code yourself. And you'd be surprised at how often this is applied in practice. And so I come from primarily a fluids background, and so my background is actually more in fluids FEM, and there's a very active and vibrant community around turbulence. And so you may have heard the term turbulence from your fluid mechanics class, but turbulence is something that's very, very difficult to model. And so people are always coming up with different models or different equations or different ways to kind of solve turbulence. And whenever someone comes up with a new equation, they have to write a code to solve it. And so there's all the CFD codes are constantly being revamped with new turbulence models, new turbulence equations. And so this comes up quite a bit. And and part of me is a little bit sad because just because the way that I kind of transformed this class, it's much more ANSYS based than what I used to teach it. But I used to teach that kind of transformation process so that you can learn a bit about that. But Now, what I usually tell students that if you are interested in it, I do teach graduate level FEA, and so we cover it more there than. Okay, well, let's go ahead and move on. And so that's a bit about the history of FEA. So let's talk about kind of more relevant things. So let's talk a little bit about boundary value. Right, so a boundary value problem, the way modern FEA is kind of designed is that it's primarily designed to solve, what's called a boundary value problem. So this is kind of the mathematical expression of basically of an FEA. Or another way that you can think about this is that every FEA problem or every FEA analysis, you can express it as a boundary value problem. And so it's useful to kind of talk about boundary value problems because the different components of a boundary value problem kind of almost have like a one-to-one correspondence to how you set up an FEA. Okay. And so there are three kind of components of a boundary value problem that I want to go over. Right, so the first component is the domain. And so the domain is basically the subject or the geometry of your analysis. And so it defines the general size, the general dimensions of where your analysis is going to take place. And so for most of this class, your domain is mostly going to be defined by your CAD file, just whatever geometry that you import into ANSYS. And so a little bit of terminology with respect to the domain. Okay. And so your domain is kind of broken up into two parts generally. And so there is the interior of the domain. Okay. And so the interior of the domain is usually given the symbol omega. Okay. So that's kind of like the inside, okay, of the domain. And then there's the exterior, there's the boundary of the domain, which you give a symbol d omega. Okay. And so we have the boundary, which is kind of like the shell that's around your domain. And then we have the interior, which is the insides. Okay. So the domain, I think, is the part that people think the least about when they're doing FEA. Right? And so, I think people kind of have the impression that you think about the domain or you think about the geometry when you're making the CAD file. And then, once you kind of get to FEA, then you just kind of do CAD on whatever domain is. Okay? But it's actually very useful. And in fact, it's sometimes it's necessary for you to really think about, what should the domain of my analysis, what should it be? For example, right? And so, for example, when you make a CAD file or when you make a CAD geometry for a certain part or an assembly, usually you CAD up the entire assembly, right? And that's useful because oftentimes you want to generate or you want to manufacture the entire part. Okay? But oftentimes it's kind of unnecessary and it's kind of a waste to run an FEA on an entire geometry. And the reason for that is because oftentimes you want to run FEA on just the part that's going to be what I call kind of engineering interest. Okay, so there's only for example if you're designing a structural component or structural part, there's usually only one or two areas of that part that's really in danger of structural failure. And so oftentimes this means, taking your CAD geometry, you have an entire assembly and just focusing on just kind of one small part. Okay? Maybe just the key supporting beam of a building, or maybe just a key part of a bridge or something like that. Okay. And the reason for that is because, we did a little bit of experimenting of this in the activity on Thursday, which is, when you get to the meshing, right? And so the meshing, has a very big impact on the quality of your FEA, right? And if you try to mesh an entire assembly, you're going to have a lot of what I call wasted elements because, a lot of those elements aren't actually going to be solving for any stress because there's nothing happening. So let's say that, you're designing a whole bridge. That's a bridge, okay? Don't make fun of my drawing. My wife does that enough, okay? But let's say that, you just kind of based on intuition that the bridge is most likely to fail in this area right here, okay? And so when you go to run your FEA, it's kind of a waste to kind of create a mesh for this entire bridge when the vast majority of the bridge, is already going to be fine, right? And so if you try to mesh your bridge and put a bunch of elements over there, those elements are basically not going to be doing anything because, they're going to have very, very little stress, okay? And so it would be a better idea to take your domain and kind of break it down to just the section where the stresses are going to be high, where you want to focus your analysis, just so that you're a little bit more smart, you're a little bit more judicial in terms of where you apply the mesh elements. Okay. And so we'll be going over a lot of this, throughout the class, but thinking about your domain, you know, I mentioned this because, you know, people almost never think about their domain. And so, you know, thinking about it and saying, you know, what's the best domain for my analysis or what I'm trying to accomplish, you know, that's something that's really important. Okay. All right. Any questions on this? All right, so the domain is the first component, and so, you know, that's kind of where you start a lot of times when you run an FEA or when you're setting up a boundary value problem. All right, number two. Number two is the governing equations. And so after your domain is established, and so after you kind of know, you know, where you're solving your equations, you want to know, you know, what equations are you actually going to solve. Okay. And so the governing equations are going to determine the type of physical behavior that you expect to solve for in your domain. All right, and so in ANSYS, you know, the way, you know, where you choose this is when you choose the type of analysis system that you're going to run. Okay. And so are you going to be solving a structural problem, that you should, you know, choose a structural system? Are you going to be solving a thermal problem, that you should be solving a, you know, thermal system? Choose a thermal equation. So those are the main three categories, at least for mechanical engineers, that we like to solve for. So it's either going to be structural, thermal, or fluids. And so, you know, you want to make sure that you choose the right one. Okay. Okay. And so, you know, again, you know, it's not like you actually see these equations, right? So you're not actually solving the heat equation, you're not actually solving Navier-Stokes or anything like that. The computer handles all that for you, but what the computer does need to know is that it needs to know what types of equations that you want to solve for on your domain. Okay? And that's why this choice is very important. And like I mentioned before, is that, you know, you're not just limited to just, you know, these types of equations. Oftentimes you want to solve for multiple things at the same time. You can have a multi-physics type of situation. And so, for example, you know, one common one that I see in the final projects for this class is solving for both thermal and structural at the same time. Right? So maybe you're designing a part that's designed to be kind of heated very rapidly. Okay, and as the part gets heated, then its material properties are going to change. So its Young's modulus is going to change, its density is going to change, because all these properties are sensitive to temperature. And so being able to model both the thermal component as well as the structural at the same time, you know, is something that's very important to do. Okay. And so we'll go over that a bit later, but, you know, whenever you're starting an FEA, you need to think about what type of governing equations or what type of analysis do I want to run, and then make sure to select the right. Again, something that seems very obvious, but when you kind of see how many options you have in ANSYS, you want to make sure that you choose the right one. Otherwise, you're not going to get the results that you get. Okay, so that's the governing equations, and so the next component for a boundary value problem, which is probably the most important for our class, is the boundary conditions. Okay. And so the boundary conditions, mathematically, what they determine is they determine how your solution will behave on the boundaries of your domain. And so physically, the way that you implement these are all the loads and constraints that you apply. Okay. Another way to think of boundary conditions, and I think the way that's kind of most useful for people is that you can think of the boundary conditions as all of the external effects or external factors that are acting on your system that you're not directly modeling. So anything that's external to your system, you can account for them in the boundary conditions. All right. And so, like I mentioned, the boundary conditions, the way that we're going to apply them, just because we're working with structural mechanics for the vast majority of the class, we think of the boundary conditions as the loads and constraints that we apply on our system. So if you have an external force that's being applied to your system, or maybe your system is being bolted or fixed to a certain location, okay, the way that you account for these is through the boundary conditions. Okay. And so, most of the time, the boundary conditions that you apply is fairly straightforward, right? And so you have an external force of 5,000 newtons. You can apply that directly onto your system. But sometimes you may have situations where the boundary conditions, a lot of times you kind of know that there should be a boundary condition somewhere, but how you actually model it or how you actually put it into ANSYS is not clear. Right? maybe you're not 100% sure exactly how much force is being applied, or you're maybe not exactly sure of the direction, right? Or maybe you're not even exactly sure, if the force is being applied there at all, right? And so it really depends on your situation, right? So let's say that you're designing a very tall building like this, right? And so one thing that you have to account for is the force that's being applied due to atmospheric winds. Okay? And so you may be wondering, should you design your building for, maybe the worst kind of gust? Maybe you have a hurricane that's just kind of randomly blowing through California for some weird reason, and you want to design your building to kind of account for that. Or do you do kind of a more typical day where the wind is blowing, much more gently, right? And so, determining, what types of boundary conditions that you apply is something that's very important. Okay? And in fact, if you get the boundary conditions wrong, or you get the load incorrect, or you constrain it in the wrong place, it can actually give you very wrong results. Okay? Which may seem like an obvious fact, and so it's like, yeah, of course, Dr. Trent, you have to do things correctly in order to get a correct result. Duh. But I think one thing that we're kind of used to when we're working with computer software is that if we make a mistake, the computer oftentimes will tell us that you made a mistake. The thing with boundary conditions is that if you apply your boundary conditions incorrectly, the computer is not really going to tell you, that it's the wrong thing, right? And so, for instance, let's say that you're designing a bridge, right? I'm not going to draw a bridge again because I'm already embarrassed from the first bridge I try to draw, right? And let's say that you want to model the force of the cars that are being applied onto the bridge, right? And so let's say that you're running this in ANSYS, but let's say you accidentally apply the force from the cars going vertically upwards instead of vertically down, right? And so that's a big mistake, and so that's gonna give you very wrong results. ANSYS is not going to tell you that you got that direction wrong, and so it's going to think that, oh, there's just a force here that's being applied up towards space for some weird reason, and it's going to run your simulation, right? And then you may take that simulation and you may think, oh, my bridge is good, and so the force is being applied in the wrong direction. Okay? And so it's very important that you kind of look at when you're doing a more complicated FEA, to look at all your boundary conditions and making sure that they're applied, with the right amount of force, that you're constraining your subject in the right way, that you're applying the force in the correct direction, all those things, because very rarely that if you apply the boundary conditions incorrectly, is ANSYS going to tell you. Okay. But of course, their boundary conditions are very important. Okay. Any questions on this? Okay. All right, so let's talk about the governing equations a little bit, and let's give a little bit more context in terms of the types of equations that we typically see in mechanical engineering, and what they look like mathematically, and what ANSYS is exactly going to solve. Let's talk about the types of governing equations that we can use. All right, so we're gonna go over three. So these are, I think, the three most common ones that you'll see in mechanical engineering. And so the first one I want to go over is our usual structural equation, which is linear elasticity. And so linear elasticity, these are equations that determine how solid objects deform when they're being subjected to external load. And so the exact equation that we solve for looks like the following. So we have the divergence of the Cauchy stress plus a body force vector F is equal to the density times the second derivative of the deformations. Partial squared u, partial x squared. Third. Right, so very complicated differential equations. Remember, we're not actually solving these, these are actually solved for in the computer, right? But if you actually wanted to solve for, the deformation distribution within a structure, this is how you would do it. Okay. Okay. And so of course, under linear elasticity, what that basically means is that the relationship between stress and strain within a structure is purely linear. If stress is equal to Young's modulus times the strain. Okay. Stress strain relationship. Hopefully that equation is familiar to you. And so linear elasticity is great. Relatively speaking, even though this differential equation is complicated, compared to some of the other equations that are out there, it's relatively simple. Okay. And relatively easy for your computer to solve compared to other stuff. The downside to linear elasticity, or static structural, as ANSYS calls it, is that it's really only valid for small amounts of deformation. And so if you look at a typical stress strain curve, typical stress strain curve looks something like this. So you have a linear region, and then once you kind of reach a certain point, then you go to plastic deformation, right? And so linear elasticity is only valid in that first linear region when the strains are small. Yeah.
Is this why, like, on our exercises, you'd have us get to like these insane values? Cause is it just following it linearly?
Exactly, yes,
If you get that, like, the metal would have sheared long
Exactly.
ago.
Yes, yeah, so that was my next point, and so when you, when we're running these static structural simulations, it assumes that it keeps this linear relationship all the way through, and so when you're getting very large deformations in ANSYS with static structural, that's actually usually a good indication that you should probably run a different equation, because static structural assumes this kind of linear relationship. Yeah. I apologize, I must have missed your hand earlier. Yeah, so there are ways to account for large deformation within ANSYS. But that gets into kind of some more nonlinear stuff. So there's kind of a relatively simple thing that you can do. And so if for your final projects, if you are seeing large deformations, we can kind of talk about it. But for at least all the activities that we're going to do in this class, we're going to be kind of in this realm of kind of relatively small deformations. Okay. Right. So that's one thing that's important to check. Whenever you're using static structural, you want to make sure that your deformations are relatively small. And what defines small deformations? Let's talk about that kind of in the next activity. Okay. But there's kind of a good eye test that you can do to determine whether your deformations are small. All right. Any questions on this? Okay. All right, so that's static structural, and so that's probably the one we're going to use the most in this class. The next most common one that you'll see as a mechanical engineer is thermal equations. So these are heat transfer equations. But heat transfer equations, these equations determine how heat or energy kind of propagate or move throughout a physical system. And what you're solving for from the heat equation is you're solving for the temperature distance. And so the equation, the equation that I showed at the beginning of class today, that involves convection as well. But when you're solving for a steady state thermal within ANSYS, most of the time you're solving kind of just the conduction problem. Okay. And so the equation looks something like the following: K times partial squared of E partial x squared plus partial squared T plus y squared plus partial squared T partial z squared. Okay. is equal to sum q x, y, z. Okay. So mathematically, interestingly enough, the heat equation is actually much easier to solve than the structural mechanics equation. So, if you ever take, let's say a graduate level finite element course, where you learn how actually the FEA method actually, comes up with that algebraic system, most of the time you're actually going to be working with the heat equation just because it's a lot easier to solve. It's very, you only have second order derivatives, which is actually quite simple. Okay. All right. And so another name for this equation that you might find in the literature is this is sometimes called either the Laplace equation or the Poisson equation. Because this is actually one of the few partial differential equations that you can actually solve by hand. And so if you take the course, I believe it's 438 or 538, if you're a grad student, then you'll actually learn how to solve this equation, which is really interesting, actually. Very difficult, but very interesting. And so we won't do too much with the thermal equation. I think I have one lecture dedicated to it at kind of near the end of the course. But just know that this is an option within ANSYS. And then kind of once you kind of learn how to solve the structural equations, how to set those up, the thermal equations are actually a lot easier to solve. All right. Any questions on this? Okay. All right. And so the last equation that mechanical engineers typically work with and when they use FEA is fluids. And so the fluid flow equations, you may be familiar with them. These are the Navier-Stokes equations. And so these equations determine how fluid will flow inside a domain when they're exposed to pressure or gravity. Right, so some of you may be familiar with the term CFD or computational fluid dynamics. And so this counts as CFD, and so you can use FEA to solve for fluid flow, and that would technically be computational fluid dynamics. Okay. And so I say that this is just one form of CFD, and so it's actually not the most common form, because there's more than one way for you to solve the fluid dynamics equations using computers. And so FEA is one form, but it's probably not the most. I don't think it's the most common. So the most common form would probably be finite volumes, and so that one is more common. And so I think some of you have experience with a software called OpenFOAM. And so OpenFOAM uses the finite volume method to solve for the fluids equations. And actually, so next semester, if you're still going to be around next semester, I know that Dr. Myral's been working on a CFD course, that he just proposed, last semester, so. I think the plan is for him to teach it in the spring, so, if that's something that you're interested in, then definitely check it out. We're gonna touch on FEA for fluids a little bit at the end of class, but you know, it's definitely not an emphasis. And so if CFD is something that you're interested in, I would definitely recommend you check out that course. I don't know if he's decided on a number yet, but that's you know, that's what that is. Okay, so the governing equation for fluids is going to be the Navier-Stokes equations. So that's partial U, partial T, plus U, partial U, partial X, plus B, partial U, partial Y, is equal to minus 1 over rho, partial B, partial X, plus nu, partial squared U, partial X squared, plus partial squared. So I really like the Navier-Stokes equations, and so like I mentioned, my background is actually in fluid mechanics, but it's been, I think, 3 years since I've taught the fluid mechanics course here, and I miss it every day, and I miss it a lot. I miss it so much that I've named the Wi-Fi in my home, I've named it Navier-Stokes, and so my wife will always say, like, why is that some kind of dirty engineering joke? I'm like, no, it's the name of the fluids equation. It's really cool. She still thinks it's some kind of weird kind of dirty engineering joke, but it's not. It's this equation. But yeah, I miss it. But you know, this is as close as I can get to teaching fluid mechanics, and so I'm enjoying this this moment. Okay. All right, and so if you want to run CFD within ANSYS, so ANSYS actually doesn't solve fluid flow itself, and so ANSYS will run another program called Fluent. Okay. And so if you kind of notice from the activity last Thursday, you know, when we actually went to actually mesh and solve our structural equations, ANSYS used a program called Mechanical, or ANSYS Mechanical. And so the fluid solver is actually in a different software called Fluent, right? And so I think I'm still not 100% sure, but I think what happened was that Fluent kind of existed as its own software for a while, and then ANSYS just kind of bought the company, and so you know, and then it just made Fluent part of ANSYS. So you know, that's kind of why it exists kind of how it is. Okay. Right. So we have three main equations. We have structural, we have heat transfer, and we have fluid. And so these are probably the three main ones that you're going to see as an engineer, as well as a few other smaller ones as well. So you know, throughout this class, we'll be learning things like vibration analysis, modal analysis. So I think that generally is very useful, but that's kind of a spin-off of the structural equations. But you know, these are the main three that you'll see. All right. Any questions on this? Yes.
You know that it's like ANSYS is a combination of programs. Are you able to like, can you just use Fluent by itself?
So even though Fluent is its own separate program, it still relies on ANSYS to do the meshing, as well as kind of setting the material properties. And so you know, you have to go through ANSYS workbench. So and so I think, you know, kind of once you get a little bit better, I think you can solve it. You can save things as just purely like a Fluent file. But generally, the easiest way to get it to work is to go through ANSYS workbench and go. Right, any other questions? Okay, all right, and so the last thing I have here is just multi-physics stuff, but we've already kind of talked about that already. So, you know, that's it for the lecture today. And so remember, if you're on the wait list, you know, hopefully by Thursday, I'll have an answer for you, but I did request that to add everyone, so, I'll give you guys an update. So thank you guys for coming today. I hope you guys enjoyed the rest of your day. It's really hot out there, so please make sure to stay cool, stay hydrated, okay? And I will see you guys on Thursday.
I need to change my shirt, my pants, I think it's like.
I do kind of add some stuff. But I largely all of them. I know it's not a place that's like. I know some people down. So there's two. Line 40 is kind of more advanced. Yeah, so we cover a little bit of theory there. 541 is the one that we go back and forth. My side. Yeah.
It'll be like about an hour. So did you see my face? My face is burned. It always is. Yeah.
Also, so in the activity there's you didn't go over the plan. You notice see that and so actually for this one here, I think I should say I want you to slide into the line. Not every Thursday, it's almost Thursday. Every other Thursday, yeah, so not this Thursday, but yes. I have to check, but that they took it down. I haven't checked it this week.
Always say.
Oh, but.
Kevin, how about behind you?
Oh, yeah, that was-
really, okay.
Yeah, so oh, yeah, and also the best is not. But you have. to-
Yeah, so the guy that set it up.
I know, I think.
And so, I don't, but I imagine, my impression is that it's not that hard to. But I think maybe this.
So. That's great.
Yeah. Oh,
I know, really.
I see, okay, I mean, to be asked, okay, so I wasn't aware.
Oh.
Yeah, let me.
Normally I would just screenshot.
Sure.
Have a good day, man.
Maybe tomorrow around. For the formation. Go back, say image to file. Or click OK.
Okay, and then you can say, oh, okay. Nice. Better than a screenshot, huh?
Oh, yeah. Yeah, for sure.
Yeah, I need to do this tonight. Oh, you have, your lab was today, huh?
What?
Yeah, your lab. I had work today.
Oh, yeah.
Oh, today. Did you finish the lab one, like, lecture?
No, he told us we can do that.
Oh, no way.
Yeah, he told me. Didn't go like here.
Yes, yes, so generally I want all.
Oh, you know, that makes sense, then, because.
You got. We started.
Yeah.
But I wanted to double check.
We did that with us, marked up.
Uh-huh.
Yeah.
Yeah,
It's much harder to use, Ansys has a graphical user.
So like in the void, we did everything except like
Open
the
phone
last
is
section.
just working forward.
There's like one last section on the bottom.
Yeah,
That's all we have.
it's a awkward thing.
Let me see.
So I don't have that much experience with open phone, and so Dr. Myral would be the one to ask about that. But I've done a few tutorials with open phone. My impression that you have to kind of create its own folder with every job that.
I'm trying to see where is like handout.
Yeah. Hey Jared, what's up?
Oh, here we are.
Oh, good to see you.
Transferred into,
We still working.
Oh, good. Great. Okay.
We are not done.
Yeah.
He said he was gonna be working on it.
Right. Yes.
yeah, I heard that.
Send me an email to remind me, so.
I also sent a message in this way.
Yeah, that's fine too. Yeah, so I was hoping, I mentioned earlier today that I put in the request on Friday. List, but the department's working on fire classes. It's most senior design on campus, because there's kind of been some stuff. Exactly, so I think, so they said they're gonna make sure we get settled for that first. But the kind of, the thing that kind of complicates things for this class in particular is that there's logs that I'm taking. Yeah, and so, you know, if everyone's added, that's about 51 people for the entire class. Which for me is not a problem, because I thought, I've done it before, but I think that the bigger issue is that for the other electives that are in this time slot, they have a lot less students. And so for funding reasons and for kind of accreditation reasons, it's better if all of the electives are kind of equal. It doesn't have to be exact, of course. But okay. Okay. Yeah.
That's why
But at this point, you know, it's already happened too. If we were to tell those 16 students that they have to switch to the other one, then they've already missed out on a week and a half of this stuff. They've been attending this conference.
it's like 1 week.
Yeah, but I'm hoping it gets resolved.
Lecture specifically. Where's you?
Answers. Yeah.
That posted?
Yes, yeah.
Cause I wanna. The canvas.
Oh, for sure. Yeah. So send me an email just to remind me, because a few people need to get it to Canvas, and then just so you can get access.
And then,
Yes, yeah.
She makes sure I got it.
Yeah, it dropped the lowest one, but then even then, you still turn in the homework late too, so, you know, 10% per day.
Cause it's Friday night, right?
Yeah, right. It's a very short, it seems like it's long just because I went through just step by step, but it's very short. So like if I were to do it from start to finish, it'd probably take me 5 minutes. There's not that much clicking, there's a lot of explanation because it's the first. It's very short.
Thank you.
Yeah.
I'll try to remember to send that email.
Okay.
See ya.
Oh, this is.